Okay. Let us start with the session. Yes, I'm putting it on presentation mode so we can actually see what all is there in store for us in this session. So let's hope we learn maximum from this session. So before we actually get into the session and know the nitty-gritties of gravitation, first let us know about our platform, that is Swiflearn. We call it the most sincere learning destination because yes, the people, the teachers who are on this platform are absolutely sincere. The customized programs, lecture series, slides that are put up are absolutely wonderful. It is 100% live interactive classes. We have one-on-one classes as well as a maximum batch is around 6 to 1 teacher. So you can imagine, you can decide which one would you prefer so that you can actually have a wonderful experience out here. We have a dedicated team of academic mentor team, as we call it, who actually track the entire progress of the students and really work on it so that we can get the maximum from the students. It covers all the syllabus as per school exam schedule. So nothing is left out, nothing is missed out. You are going with the school. So isn't that wonderful? A wonderful way of learning, I would say. Right. Our key features, if you want to know, we give detailed progress reports so you are in touch with whatever is going on. We have our Swiflearn academic test series. We also call it as the SATs. So you are assessed periodically with these test series. We take unlimited practice tests and also subjective tests with respect to the school exams. So that means we prepare you in all aspects for your exams. Isn't that wonderful? So along with learning, you're also preparing yourself. Right. So one thing that you know, if you want to know everything with respect and you want to keep abreast with all that is going on, you want to have all the notifications with respect to my lectures, subscribe to our channel at Swiflearn, press the bell icon because every time any notification comes up, you will not be left behind. So you will be notified every time and you will get an update of it. So very simple, subscribe, like, and also comment, no doubt about it, because we are here to take all your doubts and clear all your doubts and press the bell icon as well. This will keep you notified about any updates. It could be my lectures or any other teacher's lectures. So yes, let's start to our invigorating and experiential session. Right. We're going to talk about gravitation. So let's talk about gravitation. We have heard about gravitation. We've talked about gravity in all the lower classes as well. So let us start with this. Yes. So what are we going to learn in today's session? What all are the things that are going to be tackled today? We're going to talk about gravitation in general. We'll be talking about the universal law of gravitation. We'll be talking about importance of this universal law, which was put forth long back, but yes, how it is applicable today and what is the importance of this particular law. We're going to talk about free fall. What is free fall? About free falling objects and all the various changes and the effects on this free falling object. We're going to talk about how we are going to actually determine the value of g, that is acceleration due to gravity. Yes, a lot of learning is in store for us. So let us begin. And also we're going to talk of motion of the objects under the influence of the gravitational force of the earth, because whenever we talk of gravity, we think of the earth. And it is because of this gravity that we are able to stand on the earth, right? Without falling or slipping off. Okay, so let us first discuss. We know that anytime, you might have experienced it so many times, you play football, you play cricket, whenever any object is thrown upwards, it will reach a particular height. But after that, it's not that it will just go out away, far away, right? It will start falling to the ground. Now, have you noticed this? Why does this happen? Right? This is something which we have to think about. We also know whenever the apple detaches itself from a tree, it falls to the ground, right? And this is exactly the phenomenon which led Newton to actually think of why exactly did the apple fall on the ground when it detached itself, because he was sitting under the apple tree. So this was observed by Newton as well, and he started thinking about it. Why exactly is it the apple is falling to the ground? Why did it go in any other direction? Yes, and this is what makes great minds think, puts them into thinking, and this is how we talked or we came across gravity. Yes, we are also going to discuss some simple things. Now we're going to connect these two things. One thing is a falling apple, how it falls to the ground itself, nowhere else. And any object which is thrown upwards always falls towards the ground. So these are the things which should always put us thinking. So that brings us to the topic, which is today's discussion, and that is gravitation. So we know that the apple and any object which is thrown upwards always falls towards the ground because of a force exerted by the earth, which we call as the gravitational force. And the gravitational force of the earth is nothing but the force by which earth attracts all objects or all bodies towards itself. And it is exactly because of this gravitational force that we are very easily able to walk on the surface of the earth. So yes, among the all the different types of forces that are there, gravitational force is one force which is not a very strong force. It is a weak force, but yes, it can show its effect definitely. Right. Some more about gravitation. So the question that comes next is, if all the objects are attracted towards the earth, why isn't that the moon, which is a satellite of the earth, doesn't fall towards the earth? A valid question, right? Why doesn't the moon come and crash on the earth if it is the earth which is pulling objects towards itself? Right. Let us actually understand this by carrying out a simple activity. Right? So what is the activity? Let us start. Just imagine you have tied a small stone to a piece of thread, and the stone is at one end of the thread, and now holding the other end, you start whirling it over your head round and round and round. How does the stone move? Have you noticed the motion of the stone? Yes, it goes round and round over your head. Right. Now, if you release the thread, you leave it, or if you give a cut to the thread, what would happen? And then notice what would happen to the stone, which direction. This is exactly what we're talking of. This is how it will move, right? And before the thread was released or it was cut, the stone moves a circular path. Can you see this? This is because of a force which we call as the centripetal force, which is acting from the center. If this centripetal force would not be there, the stone would fly off in a straight line. So many a times if you would cut the string, what you would see that the stone would go tangential to this path. Right. So when we are talking on gravitation, this is exactly what happens with the moon as well. The motion of the moon around the earth is because of this force, which we call as the centripetal force from the earth, which is the force of attraction from the earth. And it is this centripetal force which lets the moon continue to revolve around the earth. And that is why the moon does not crash towards the earth. So there is a force called as the centripetal force. So that is the reason why moon does not crash on the earth, in spite of earth exerting a force of attraction on it. Now let us move ahead. This is Newton, and this is exactly how Newton was put thinking when an apple fell on his head. And then he realized that why is the direction of the apple directly on his head? Why it is moving downwards, right? So this is what he started thinking. All right. So does the apple get attracted only towards the earth? Another valid question. Or is it that the earth is also attracted towards the apple? Right. Okay, we are talking about a force of attraction between two bodies. So if earth is also a body, of course, and if the apple is being attracted towards the earth, definitely the earth also must be getting attracted toward the apple, right? Yes. This is a simple thing. When we talk of Newton's third law of motion, this exactly comes here, that every action has an equal and opposite reaction. So the apple also attracts the earth. But we never see the earth moving towards the apple as we see the apple moving towards the earth, right? Why is that so? Now, this is because there is an answer to this. Newton's second law of motion, which states that Acceleration is inversely proportional to the mass of an object for a given force. Now, this might be force of attraction as well. That means lesser the mass, more is the acceleration. So if you would really compare the mass of the apple with the mass of the earth, now we can realize that the mass of the apple is absolutely negligibly small as compared to that of the earth. So the acceleration produced on the earth by the earth because of the attractive force from the apple is definitely very, very less because its mass is more, much more as compared to the apple. And that is why Earth shows less acceleration than the apple, and therefore we cannot see the Earth moving towards the apple. Now things are getting clear, right? So we are able to connect mass of a body with acceleration, right? Whenever we consider force. Okay, so one thing we know, the gravitational force of the earth, we also call it as gravity, is responsible for many, many things. And it is so, so good. It's such a helpful phenomenon, a helpful force of attraction. It holds the atmosphere above the earth, the mixture of gases which forms an envelope around the earth. And it is very, very helpful for us. It's a mixture of various gases. And this atmosphere is held in place around the earth because of this gravitational force of attraction exerted by the earth. The rain falls towards the earth. So whenever the clouds are formed over the earth and there is precipitation comes down as rain, this rain comes down towards the earth because of the force of gravity or the force of attraction exerted by the earth. Lucky, aren't we? Also, the flow of water in the rivers. Rivers flow on the surface of the earth because of the force of gravity, that force of attraction, which keeps them on the surface and they flow very easily. It helps keep us firm on the ground. Otherwise, we would be constantly slipping if there would be no force of attraction exerted on us and we are kept in place firm on the earth, standing. Also, the revolution of the moon around the earth. We have already talked about that. And as a result of which, moon does not crash on the earth. So yes, gravity or gravitational force of attraction is very, very important for us. Okay, let us answer a few questions. Why do things fall down when you throw them or drop them? We just discussed this. So it becomes so easy to answer these questions now. Things fall down because of an invisible force, which we call as the force of attraction due to the Earth's gravity, which pulls objects towards the ground. And that is the reason why anything you throw up always comes down, right? We did learn about this right now. All right, so let us now talk about the universal law of gravitation, which is applicable to the entire universe. It becomes a standard for the entire universe. So what is the universal law of gravitation? Okay, it says that every body in the universe attracts every other body with a force and which is proportional to the product of their masses, the masses of the two bodies. It is directly proportional, whereas it is inversely proportional to the square of the distance between them. And what is the distance? How do we calculate? It is not actually the entire distance. We take the distance from the center of the two bodies. The line joining the centers of the two objects is calculated as the distance. So simple, if I'm having an object A with, say, it looks a little bigger, let's take its mass as capital M, another smaller object with mass small m, and the distance between them, can you see, is B. Then what it says that force is directly proportional to the product of their masses. So it is directly proportional to capital M into small m, and inversely proportional to the square of the distance between them. So what we are seeing is F, we'll take that as a force of attraction, directly proportional to the product of the masses. So we can take the first body, mass of the first body is M1 and mass of body 2 as M2. So we are talking about the force of attraction. One thing is it is directly proportional to the product of their masses. And the second thing is it is inversely proportional to the square of the distance. We can take it as inversely proportional or proportional to 1 upon r square, or you can take it as d square as well. So now if we combine both these equations, equation 1 and equation 2, what do we get? We get F, that is a force of attraction, proportional to m1 into m2 upon r squared. We have combined both equation 1 and 2. One is a direct proportionality of the product of their masses. Another is inverse proportionality of the square of their distance. So we know that anytime we want to remove the proportionality sign and we want to put it as an equal to sign, we always put a constant. So here, when I'm converting it into an equal to sign, F becomes equal to a constant. We write this as capital G into, everything else remains the same, m1 into m2 upon r square. So here, G is called the universal gravitational constant because it is a constant here, because we have tried to remove the proportionality sign and have put the equal to sign. So what we are doing is we call it as the universal gravitational constant, capital G. Yes. So if I want to know about capital G, I will just rearrange. I said F is equals to G into M1 into M2 upon R square. So when I'm going to rearrange the entire thing, I will get the formula for G, the universal gravitational constant, as F into R square upon M1 into M2. So now if we put on the units, force is in Newton, distance is in meter square. Since it is r square, distance is in meters, so meter square upon mass is in kilogram, kilogram into kilogram, kilogram square. So the SI unit of the universal gravitational constant, capital G, is Newton meter square per kilogram square. Remember this. This is very, very important. And when we talk of it as being a constant, it is a constant for the entire universe. It is not going to change on any part of the universe, any planet. So it is a fixed value. So what is this value? The value of the universal gravitational constant, that is capital G, is 6.67 into 10 raised to minus 11. And we already know the units, Newton meter square per kilogram square. And we have to understand one more thing. The value of G does not depend on the medium between the two bodies. The medium can be anything, but this value remains constant. It can be anywhere on the universe, the value remains constant. So that is why we call it the universal gravitational constant. So value of G is the same throughout the universe. So, and the SI unit, as we've already discussed, is Newton meter square per kilogram square. Right. Now, if we consider the two bodies that are actually attracting each other in the universe, if we take their mass as unit mass, that is 1 kilogram and 1 kilogram, and the distance that is separating them as unit distance, that is 1 meter, then every value there becomes 1. In such a case, the universal gravitational constant becomes equal to the force of gravitation. So what does this tell you? The universal gravitational constant, or G, is numerically equal to the force of gravitation, which exists between two bodies if they are of a unit mass. So we are talking of 1 kilogram kept at a unit distance, 1 meter from each other. So I've got two bodies of 1 kilogram mass kept at a distance of 1 meter, right? We're talking about unit meter. Then in such a case, the universal gravitational constant, G, will be equal to the force of gravitation. This is how we can manipulate and try to understand this particular value or entity. Now, why is this universal law of gravitation so very important? Because it explains to us the force that binds us to the earth. Very important. That is the first thing. It also explains the motion of the moon around the earth and also planets around the sun. We cannot forget one thing, that all the planets in our solar system actually revolve around the sun at the center. So yes, not only the revolution of the motion of the moon around the earth, it also explains the motion of all the planets in our solar system around the sun, and also talks about the tides due to the moon and the sun. We are talking of here the tides in the sea, the high tide and low tide, which we actually connect with the sunrise and sunset, the different times of the day, and also the various moon phases. We talk of the new moon and the full moon. Yes, they also have an effect on the tide. So that also explains this can be explained through the universal law of gravitation. Yes, so very handy. So let us go through some questions and answer the questions. We have already learned quite a few about these things, so let us start. We are talking about write the mathematical formula of the universal law of gravitation. We already know this. This is F equals to capital G, that is a universal gravitational constant, into product of the masses. So capital M into small m, or you can take it as m1 into m2 upon r squared, square of the distance. So here, when we talk of G, it represents the universal gravitational constant. Capital M and small m are the masses of the two bodies, and r is the distance between the two bodies. So here, it's square of the distance, so it becomes r square. Easy. Right, now they've talked about calculate. We talked of it to be a constant value, right? So how do we get this? We just substitute these values in our formula, right? So that is how we come across the gravitational force between the earth and the sun. So easy when we have the formula with us. Just substitute the values. We already know the value of G, 6.67 into 10 raised to minus 11 Newton meter square per kilogram square. So yes, it is a constant value anywhere in the universe. Mass of the earth is also fixed, 6 into 10 raised to 24 kilograms. Mass of the sun, we also know, 2 into 10 raised to 30 kilograms. And the distance between the earth and the sun is 1.5 into 10 raised to 11 meters. So yes, we have all the values with us. We just have to substitute the values in the formula and we get the value of F. Isn't it easy? Yes, it works out to 3.56 into 10 raised to 22 Newton. My suggestion is get all the 10 to the power of 10 raised to values to one side and calculate them separately, and all the other values separately. You will be able to come with your answer very easily. Right, let us move ahead and talk about another person, Johannes Kepler. He also came up with his 3 laws. We call it as Kepler's laws, the first law, second law, and third law, which describes the motion of the planets. So yes, this also tells us, Kepler's laws tells us about the motion of the planets in our solar system. So we call these as Kepler's laws. So let us learn about Kepler's law once we have already known about capital G, or the universal gravitational constant. So yes, Kepler's laws. The first law. So who was, it was Johannes Kepler who gave us the 3 laws, which explains everything about the motion of the planets. The first law is the law of the orbit. As you know, orbit is the invisible path that the planets take around the moon, right? So what did he talk about these orbits? The law of the orbit, the first law, Kepler's first law, said that each planet moves around the sun in an elliptical orbit with the sun at one of the foci of the ellipse. An ellipse, can you see this path? This is an elliptical path, and the sun occupies one of the foci, one of the locations in this particular orbit. So each and every planet moves in an elliptical orbit around the sun, right? That is the first law, Kepler's first law. We also call it as the law of the orbit. Okay, now based on this law, we can say that the planet which is closest, when the planet is closest to the sun, because we talked of it being an elliptical orbit with the sun at one of the foci. So when it reaches a place where the distance is less, it is closest to the sun, here the speed is maximum, the planet moves faster. And when it is at the farthest, far away from the sun in this orbit, that time its speed is minimum. This is what this law actually says. So that was the first. So here when we talk of this, it states the second law, that the line joining the sun and the planet, if you join the planet and the sun in this orbit, it sweeps out equal areas in equal intervals of time. So if we take sun as S, then here can you see two areas? There is NOM, this is one triangular area, and there is LOK or KOL. Now if you see these two areas, it says that area of NO1M is equal to area of KO1L, both these areas. So in this orbit, as it is moving around the sun, each planet actually brings about equal areas, it carries or sweeps equal areas in this orbit in equal intervals of time. So this is what exactly it says, that closer it is to the sun, it moves faster. Farther away it is from the sun, it moves a little slower. Yes, explains many things here. That was the second law. What about Kepler's third law, a very important law? It says that the square of the period of revolution of the planet around the sun is directly proportional to the cube of the semi-major axis of this orbit. So this is what we are talking about, the axis of the orbit. So simple, if we consider this as an elliptical orbit, the time period, square of the time period is directly proportional to the cube of the semi-major axis. So we are taking that as r. So t square directly proportional to r cube. Understand this. So we have got three laws of Kepler, which very well explains the movement of the planets or the revolution of the planets around the sun. Okay. All right. So let us visualize what we are trying to understand here. Sorry about that. Okay. So let us answer this. All right. What does it say? State Kepler's third law. This is how you will get your questions. State Kepler's first law. Third, we know first law talks about the law of the orbit. Second law talks about sweeping equal areas. And third talks about linking the time period with the axis, right? So Kepler's third law states that the square of the period of revolution of the planet around the sun is directly proportional to the cube of the semi-major axis of this elliptical orbit. So how would you put it in the form of a formula? It would be t square directly proportional to r cube. Yes. Now we have learned about Earth attracting objects towards itself. So now let us talk about fall of the objects when it occurs only under the force of gravitation. So I am having an object which is just falling down, and the only force acting on this falling object is the Earth's gravitational force of attraction. So what is this called? We call it as a free fall. So what does free fall actually mean? When any object is falling towards the surface of the Earth and the only force of attraction or force acting on it is Earth's gravitational force of attraction, we call it as a free fall or a free falling object. Okay, so this is how it is. Can you look at this? There's a feather also falling and a ball as well. So when a body falls from a height towards the Earth, only under the influence of the gravitational force, and there are no other forces acting on it. Understand, here we are talking about no resistive force of the air, nothing. Then the body is said to have a free fall. This is very important. Only force acting on it is the gravitational force exerted by the Earth. Okay. Here. This is also free fall motion. You must have seen people jumping out of the aircraft, and for a pause or for some time they are just suspended in air, and then you can see them coming down, falling down. That is free fall motion, because it's the Earth's gravity which is acting on them, which is attracting them towards it. So now when we can think of, will there be any change in the velocity of the falling objects? If an object is falling from a height and the only force acting on it is the Earth's gravitational force of attraction, then will there be a change in the velocity? Let us see. Okay. We know when we talk of change in velocity or wherever we need to change velocity, either the magnitude of the velocity changes or the direction of the motion changes, or both will change. So either there will be change in the magnitude of the velocity, or there should be change in direction, because we know velocity is a vector quantity. So there is magnitude as well as direction. So either one of them will change or both will change, then we know velocity will change. So while falling, direction of motion of any object, it is hurtling down, the direction is going to remain the same. But due to Earth's attraction, this magnitude of the velocity definitely changes because the Earth is exerting a force of attraction on them. So because there is change in the magnitude of velocity, we can say, yes, there is change in velocity. So during free fall, definitely, can you see this? Starts from 0 meter per second because I'm leaving the object now from a height. So initial velocity is going to be 0. It is coming downwards, and can you see the change with the time period? At 3 seconds, it is 30 meter per second. When it is coming down, at 5 seconds, it is 50 meter per second. So there is definitely change in the magnitude of the velocity. Definitely the direction has not changed, right? It is moving in the same direction. So there is a change in velocity. What do we call a change in velocity? Change in velocity is, is nothing but acceleration. And this is because of the force of gravitation, or the Earth's gravitational force. So change in velocity because of the acceleration or the gravitational force acting on it, we call this acceleration as acceleration due to gravity. Have you understood this? There is change in the velocity when an object is having a free fall. Definitely. And when we talk of change in velocity, it is nothing but acceleration. And this acceleration of the free falling object is occurring because of the force of attraction or gravitational pull of the Earth. So that is why this acceleration is called acceleration due to gravity. You must have heard it so many times. And we give the alphabet for it as small g. The universal gravitational constant is capital G, and acceleration due to gravity is small g. The unit and the value is a fixed value. This is also a constant, 9.8 meter per second square. Yes. So we have learned another term now. All right, now we are going to actually determine the value of this g. How did it come about to be 9.8 meter per second square? Now we know from Newton's laws that force is equal to mass into acceleration. And we also know that force, the force of attraction, gravitational force, is equals to capital G into m upon r square. Now since both here are the same force that we are talking about, so both these will be equal. So gmm upon r square is equals to m into a. The small m gets cut from both sides. So what remains is g capital M upon r square is equals to a. So what does this mean? What I'm getting is gm upon r square is a, which we know this acceleration is due to gravity, which we have already given a letter g. So small g is equals to capital G into capital M upon r square. And when we substitute the values that we already know, we get the value as 9.8. Yes, so to calculate the value of small g, that is acceleration due to gravity on Earth, we substitute the values of capital G. We already know 6.67 into 10 raised to minus 11 Newton meter square per kilogram square. Mass of the Earth 6 into 10 raised to 24 kilograms. The radius of the Earth, you can take it as 6.4 into 10 raised to 5 meters. When we substitute these values in the formula, small g equals to capital G into m upon r square. When you work it out, it works out to 9.8 meter per second square. So acceleration due to gravity, small g, on Earth is 9.8 meter per second square. So today we have actually calculated two constant values, capital G, the universal gravitational constant, and the second small g, acceleration due to gravity on the Earth. Yes, now what are we going to talk about further? Motion of objects under the influence of this gravitational force of the Earth. So when the small g is acting on any object, how will they be moving? So to understand motion of objects under the influence of the gravitational force of the Earth, small g, let us carry out a small activity. Okay, what is the activity? Can you look at this? Take a feather and take a stone and drop them simultaneously at the same time. What do you expect? What is going to happen? We will find that the feather reaches the ground a little later than the stone. Now we would expect, why should this happen? Yes, definitely. But here this happens because there is a resistance, right? There is the air currents, there is air which is somewhere, the feather being very light is resisting its movement downwards. This is the reason why the feather reaches a little bit later than the stone. So let us perform this activity in a glass jar. So now here, where the air has all been sucked out, that means a vacuum has been created here, so that there is no effect of any resistance of air currents at all. And now when we do this experiment, you can see that both the stone and the feather fall down at the same rate. Surprising, isn't it? We would expect that the stone being heavy would come down first than the feather. But no, both of them come down or fall down at the same rate. Yes, something new you've got to learn. Now, we also know the kinematic equations that were put forth by Newton, the Newton's laws of motion, right? So when we talk of value of acceleration g during a free fall motion, we know is constant. It has a fixed value, 9.8 meter per second. So all your kinematic equations of motion for uniformly accelerated motion of objects becomes valid. We just have to put the sign convention wherever we are using the equation, depending on whether it is moving upwards, it is going against gravity, we'll put a negative sign. So we'll use the sign conventions depending on the direction. So we already know initial velocity is u, final velocity is v, s we take as the distance, a is the acceleration, t is the time. Right? So u represents initial velocity, v represents final velocity, a represents acceleration, and t is the time. The kinematic equations are v equals to u plus at, s equals to ut plus half at square, v square equals to u square plus 2as, or another way of putting it is v square minus u square equals to 2as. Now, we are going to connect these kinematic equations with our free fall object, right? Free falling object, how are we going to connect it? So first, let us answer this question. What do you understand by free fall? Because we just did it. We just learned this. When an object is dropped from a height under the influence of the gravitational force, it begins to fall to the surface of the Earth. Then we say this object is having a free fall. So the only force acting on this object is the gravitational force of attraction of the Earth. Yes, so we have learned about free fall. Okay, here they've asked us to take g as 10 meter per second just to round off. A car falls off a ledge and drops to the ground in 0.8 seconds. So from a ledge, a car is falling down to the ground in 0.8 seconds. What would be the speed when it is striking the ground? So we are going to use our kinematic equations, and when it is falling from a ledge down, the initial motion is going to be 0. Initial velocity is going to be 0. U will be taken as 0. So we are going to use the formula, and what we get is the answer. You just have to put, yes, it works out to 8 meter per second because it is only going to be ut. So we are taking v is equals to u plus at, u is 0, so a into t, this is 0.8 into 10. So we are talking about t into g. Here g will be nothing but a. So this is how you will be getting 8 meter per second. We're talking of average speed, it average, so it is 4 meter per second. And how high is the ledge? So we are talking of the height of the ledge. So instead of S, we are going to put it as H. That is the height. It works out to. So S equals to UT plus half AT square. Here U is 0, so UT entity becomes 0. Instead of S, we'll take it as H. So H equals to half into A. Here A is acceleration due to gravity. So let's put it as G. So half into G into T square. So half into 10 into 0.8 into 0.8 works out to 3.2 meters. Yes. So now, what all are the things that we have learned today? We learned quite a lot of things. In today's session, we dealt with what do we understand by gravitation? We learned about gravitation, the universal law of gravitation. In fact, we also derived the value of the universal gravitational constant. We spoke of the importance of law of gravitation, how it is applicable to the entire universe, how it is applicable to the moon revolving around the earth, all the planets revolving around the sun in the solar system. We talked about the free fall, a free falling object. What is the force of attraction acting on it? We actually determined the value of small g, acceleration due to gravity. We also talked about the motion of objects under the influence of the gravitational force of the earth. So we did talk about there being a change in the velocity, but no change in the direction of motion when any object is falling towards the earth. These were many things that we learned about in today's session. Hope it was very, very interesting and also very helpful to you in knowing many of the natural phenomena that occur around us. Whatever doubts you have, please put it up in the comment section. Do subscribe to the channel and definitely leave your comments, what your doubts are on the comments, like and subscribe the channel. Thank you so much. We will meet again on the same platform of Swiflearn. Once again, learning, getting more facts about gravitation. Thank you.